Hello friends, welcome to lecture on dynamics of fluid. In earlier lectures, we have seen the fluid statics and fluid kinematics, the important branch of fluid mechanics. But fluid mechanics study will not be complete until and unless we study dynamics. So in dynamics, we are going to give focus on the motion of the fluids and the forces which are responsible to cause the motion. Here in dynamics, we are going to consider motion with forces. So here the dynamics is based on the Newton's second law of motion, and which states that the resultant force acting on any object is responsible for its momentum, or resultant force is nothing but rate of change of momentum. Or in simple way, we can say that if Fx is the resultant force acting, then it is equal to mass of that element, fluid element, into acceleration happening in that direction. So let us consider it is a Fx direction, and according to the Newton's second law of motion, Fx is equal to m into ax. Now this fluid resultant force acting on a fluid flow is the sum of different forces acting on fluid flow system, and these forces are the gravity forces, summation of gravity forces, pressure forces, viscosity forces, turbulence forces, and compressible forces. Then the resultant force acting on a fluid flow system, we can say it as a resultant force acting on a fluid flow system, we can say it as a so is equal to Fx is equal to, if Fx is the resultant force acting in x direction, is equal to gravity force acting in x direction plus pressure force acting in x direction plus vibration viscosity force acting in x direction plus turbulent force acting in x direction plus compressibility force acting in x direction. And if the force of compressibility, if we neglect Fc, then Fx is equal to Fg of x Fx, Fp of Fx plus Fu of Fx plus Ft of x Fx, and this equation is called as Reynolds equation. So in Reynolds equation only we are considering pressure force, gravity force, viscosity force, and turbulent force. Again, and if we neglect the turbulence force, then whatever the equation we will get, that Fx is equal to Fg of F, Fg of x, Fp of x plus Fu of x, and that equation is called as Navier-Stokes equation. And if again we remove, in neglect the viscosity force, then equation Fx is equal to Fg of x plus Fp of x is nothing but is called as Euler's equation of motion. So in Euler's energy equation of motion, we are only considering the two forces, that is pressure forces and gravity forces. Now we'll derive the equation, Euler's equation of motion. And for this, only two forces we are going to consider. One is pressure force and another is what? Gravity force, and which is responsible to generate the weight, or it is nothing but indirectly we can say the weight. Okay. Now let us consider one particular fluid element. So let us consider the fluid element of this fluid element is there having length dx, cylindrical fluid element, length dx, and here length area of cross section dA. This is fluid element is placed in a streamline direction, yes. So this is going to be the streamline direction, yes. Okay. Now let us consider the forces acting on the fluid flow element. So the first force acting is PdA, and this force is acting in the direction of flow. And at the opposite end, the force of magnitude P plus dou P by dou S into ds into dA, that force is acting in opposite direction of flow. And another, now weight is also acting through this particular way, perpendicular to the axis of the element, and its weight component is nothing but what? Rho g dA ds, because rho g dA ds represent the volume, and volume into mass weight is equal to the weight force. So is equal to rho into g is a weight of that element, okay, density into okay, specific weight into volume is equal to weight. So this rho g dads is the weight element, and this weight element makes an angle theta with the axis of this particular element. So this rho g dads is having two components. One is in direction of streamline, that component is rho g dads cos theta, and perpendicular to this is rho g dads sin theta. But in Euler's equation we are going to consider only the forces along the streamline. Therefore rho g dads sin theta will not consider. Okay. Now here the forces are there. Pressure PDA in the direction of force. Okay. Then pressure force P plus dou P by dou S into ds in opposite direction of flow, and weight of element is rho g dads, and its angle component is rho g dads cos theta only we are going to consider. Okay, then resultant force acting. Now for that, the forces which are acting in the direction of flow we have to consider positive, and forces which are acting in opposite direction we have to consider negative. So therefore PDA minus P plus dou P by dou S ds bracket multiplied by dA minus rho g ds cos theta is the component of weight along the streamline. Then it becomes what? If we simplifies, it only become P rho dads into as. Rho dads into as means what? This is again equal to rho dads into as. This is one equation. This is another equation. Means mass into acceleration in x direction. And mass is rho dads. Okay. Where as acceleration in the s direction. And this as is equal to dv by dt. And we know that v is a function of s space coordinate s and time coordinate time t. Therefore as is equal to dv by dt, and v is a partially function of s and partially function of t. Therefore is equal to dou v by dou s into ds by dt plus dou v by dt into dt by dt, but dt by dt will become 1. But ds by dt is nothing but what? V. Okay. Therefore it is equal to v dou v by dou s plus dou v by dou t. If we simplify, is put the substitution that flow is steady, then dou v by dou t will become 0. And for steady flow, now this Euler's equation now we are applying for steady flow. As is equal to v dou v by dou s. Now substituting the value of this equation in this equation, that is equal, therefore these two equations are related to force, resultant force. Therefore this we can equate. Therefore minus dou p by this simplification, pda will get cancelled. So minus dou p by ds dou s ds dA minus rho g ds cos theta is equal to rho ds into v ds. And then after simplification is there rho ds dA minus dou p by rho ds dividing by, okay, rho ds dA minus dou p by rho ds minus g cos theta is equal to v dou v by dou s. But this cos theta, g cos theta is there. Cos theta is equal to dz by dz. If we go for the triangular element, okay, here in this case, then here cos theta is equal to, this is going to be axis perpendicular axis dz, and this is length ds, and true in between them angle, that is a theta. Therefore cos theta is equal to, we can say here it is going to be dz by ds. So you can substitution dz by ds will be cos theta. If you substitute this, then we will get equation 1 by rho dou p by dou s plus dz by ds into v dv by ds is equal to 0, or dou p by rho plus dz dividing ds will ds, or ds if we go to we will take common, is equal to 0, plus v dv is equal to 0. And this equation, that is dou p by rho plus g dz plus v dv is equal to 0, is called as Euler's equation of motion. And what is significance of this is that the in a fluid flow the pressure may change, potential energy may change, kinetic energy may change, but net change is equal to 0. So this dou p dz dv represent the change in potential, pressure energy, potential energy, and kinetic energy. And net change is equal to 0. And net change is equal to 0 means that energy of fluid flow in the always remain constant. Now from this Bernoulli equation we have to from this Euler's equation we have to obtain our important equation, main equation of fluid mechanics, that is Bernoulli's equation. So whatever the equation is there, Euler's equation, that equation we have to integrate individually. Okay, then it will be there that then we'll get the total characteristics of the flow. Now only we are getting characteristics only in the related to fluid flow element. Okay, that is net change is equal to 0, or we say indirectly total energy is equal to constant. Now, if you integrate individual terms with respect to Euler's equation with respect to individual term, so integration of dp by rho plus integration g dz plus integration v dou v is equal to integration of 0 is equal to constant. Then it is equal to constant. Therefore, integration of dou p rho is equal to constant. Again, incompressible fluid if you consider. Then p upon rho integration of dou p will become p, rho will be constant, plus g is constant, g into z plus v square, integration of v square v dv is v square by 2 is equal to constant. Then if you divide rho by both sides, then p upon rho g plus z plus v square upon 2g is equal to constant into z. G is again constant, So p upon rho g plus v square upon 2g plus z is equal to constant. This equation is called as means total energy of the flowing fluid always remains constant, and total energy includes pressure energy or pressure head p upon rho g, v square upon 2g, kinetic energy or kinetic head, and z potential energy or potential head. So total energy of the flowing fluid always remains constant. Now we'll see the remain example. So here the examples are there. Let us consider one example. Water is flowing through a pipe of 5 centimeter diameter under a pressure of 29.43 Newton per centimeter square gauge pressure and mean velocity 2. So v1 is given, p is equal to 29.43. So we convert into SI unit, 29.43 into 10 raised to 4 Newton per meter square. Diameter is given, d is equal to 0.5 meter, 0.5 centimeter. So it may be 50 centimeter, not 5 centimeter. So therefore 0.5 meter. And find the total head. Total head we have to calculate, and the or total energy per unit weight of the water as cross section, which is 5 meter above the datum line. So that z is equal to 5 meters. So total head is equal to pressure head plus kinetic head plus datum head. So pressure head is nothing but p upon rho g. Water is the fluid, therefore density is equal to 1000. Pressure is given 29.43 into 10 raised to 4 divided by 1000 into 9.30 meter. Okay, then kinetic head v square upon 2g, already v is given as 2 meter per second, so v 2 into 2 it will become 4, and 2g it will become 0.204 meter. And then afterwards what, p upon rho g plus v square upon 2g plus z, total head will become 35.204. So this equation is now useful to calculate the total energy of the flowing fluid. Means total energy of the flowing fluid is equal to pressure head plus kinetic head plus potential head. Now, this Bernoulli equation we have to apply for a real fluid and for the sections. Now, when we are applying this particular Bernoulli theorem, we have considered that the fluid is ideal because we have not considered any viscosity forces. Therefore, fluid is ideal. So there is no viscous force acting. Then friction we are negligible. We are not considering. But in real cases, when the fluid is flowing through a pipe, through any cross section, then always there is a friction in between flowing fluid and the surface, and therefore loss of energy takes place. And therefore at two sections or two inlet and outlet, the exact total energy will not be exactly same. So inlet energy, some component, some of the quantity of inlet energy is always go in the to overcome the friction, and that is called as head loss or head loss due to friction. So if inlet energy is equal to P1 upon rho, and always remember that head loss we have to always add at outlet, because energy at inlet is always more and energy at outlet is always less. So P1, to balance the equation, head loss we have to always add at the outlet. So P1 upon rho g plus V1 square upon 2g plus Z1 is represent the total energy at inlet, and P2 upon rho g plus V2 square upon 2g plus Z2 is represent the total energy outlet, and plus some energy losses. Generally it is due to friction. So when we have to apply the Bernoulli equation for real fluid, we can say that P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2 plus HL, and this HL is nothing but what, head loss, and generally head loss is maximum, the contribution is due to friction. Now we'll see the example of the Bernoulli equation for real fluids. Okay, then they have given that a pipe of diameter 400 mm carries water in with a velocity of 25 meter per second. The pressure at the points A and B. So they have given the pipe also to us. This is a given diagram. So points A and B are 29.43 Newton per centimeter square, and at A the pressure is 29.43 Newton per centimeter square, and at B it is 22.563 Newton per centimeter square. While the datum head at A and B are 20. So for this is one datum line we consider. Then from ZA is equal to 28 and ZB is equal to 30 meter from the datum line. Find the loss of head. So loss of head we have to calculate. So for that we have to calculate the total energy at section A and total energy at section B. And which is going to be more from this is considered as inlet, and which is less that we have to consider as a outlet. And energy difference will be nothing but head loss. So total energy at A, EA we consider is equal to PA upon rho G plus VA square upon 2G plus ZA, and is equal to, if you put the substitution that we know factor here. So in SI unit 29.43 into 10 raised to 4 divided by 1000 into 9.81 plus 25 square in divided by 2 into 9.81, and this will give plus 28, it will give 30 plus 30, total head will become 89.85 meter. Likewise, here we can calculate the total energy at here B, and the energy at B is equal to PB upon rho G plus VB square upon 2G plus ZB. And here in this case, and now this pipe is uniform, therefore velocity is going to be same at both cases because pipe is of uniform diameter. Okay, therefore we have considered that VA is equal to VB is equal to or uniform velocity because pipe is of uniform diameter. Okay, then energy at B is equal to, here it is equal to so it is equal to PB upon rho G plus VB square upon 2G plus ZB, and if you substitute all the values in a SI unit, then energy at B is equal to 84.85 meter. Then energy at A means A energy is more, therefore the flow is from A to B because which head is more, and that is A head, therefore the flow will flow from A to B, and therefore loss of energy is EA minus EB is equal to 5.0 meter. Okay, now we will go for another problem. A conical tube, this is a conical tube is there of length 2 meters, so length of the tube is 2 meter, is fixed vertically with its smaller end upwards. The smaller end is upward. The velocity of flow at the smaller end is 5 meters. So V1 is equal to what? 5 meter per second. While at the lower end, the velocity is 2 meter per second. So V2, if we consider lower end, smaller end is 1 will suffix by 1 suffix, and let us consider the bigger end is having suffix 2. Okay, then we can, the pressure head at the smaller end is 2.5 meter of liquid. The loss of head, that is E1 or E1 minus E2 is equal to HL, or is equal to 0.35 V1 minus V2 bracket square divided by 2G, where V1 is the velocity at smaller end and V2 is at larger end. They are given. Determine the pressure head at lower end. Flow takes place in the downward direction. So means this flow is, this is inlet and this is outlet. So means energy at 1 is always more than energy at 2. Okay, then length of, and that we have to consider the length is equal to 2 meter. So V1 is equal to length means if you consider the atom itself at section 2, then Z2 will become 0 and Z1 will become 2. That is the use of that length. V1 is 5 meter per second, they have given. P1 upon rho G is 2.5 meter of liquid, they have given. Okay, and then P2 upon rho G we have to calculate. Then HL is equal to 0.35 into V1 minus V2 bracket square divided by 2. So V1 is 5, so we can calculate this HL. Okay, so this HL head loss is equal to 0.16 meter. Then pressure head at P2 upon rho G we have to calculate. Now applying Bernoulli equation at section 1 and 2, what we will get? P1 upon rho G plus V1 square upon 2G plus Z1 is equal to P2 upon rho G plus V2 square upon 2G plus Z2 plus HL. But HL value we know 0.16, and all values we are knowing. So P1 upon rho G, P2, V1 square upon 2G, Z1, all things, because that term we are considering as a point number 2, that is bottom section, therefore Z2 will become 0 and point. So if you consider that P2 upon rho is coming as 5.407 meter of fluid. So this way we have to solve the numericals on this particular Bernoulli's theorem. Now in this today's unit we have completed the study related to the forces acting on a fluid flow system, what is mean by Reynolds equation, what is mean by Navier-Stokes equation, what is mean by Euler equation. Then Euler's equation we have derived on a streamline, and afterwards we have derived the important favorite equation, Bernoulli's equation, and afterwards we have seen the applications in the numerical form of Bernoulli's equation. We have seen the Bernoulli equation for real fluids also there, where we have considered the head losses, and we have solved two numericals. So next class we will go for the practical applications of the Bernoulli theorem. Thank you for giving your patience listening for this video. Thank you very much. Thank you.